We are moving to question 23 with sub-questions. So it has different sub-questions, around 5 sub-questions for question 23. So let's start on the sub-question number 1. It is asking the energy of the n equal to 5 state. So which means we have the hydrogen atoms, and the question is asking the energy of the n is equal to 5 state. So to do this question, we know that the energy is equal to minus Rydberg constant dividing with n squared. So we can then, for n is equal to 5, so we are replacing n with 5, then we get the energy. We know that the Rydberg constant is electron-volt is equal to 13.6 electron-volt. Then if we can replace the n by 5 and the Rydberg constant with 13.6 electron-volt, then we get the answer, which is minus 0.544 electron-volt. Moving to the second sub-question. The second sub-question of this question is asking to calculate the total energy, the kinetic energy, and the potential energy for an electron in the hydrogen atom. Then it is asking to calculate in electron-volt. So we know that the total energy in the hydrogen atom is equal to minus n, which is Rydberg constant, dividing with the n squared. Then we know that the share, so hydrogen is having one share, so which means the n is equal to 1. By replacing then the Rydberg constant with 13.6 electron-volt, then we press the sign minus, then we get the total energy, which is minus 13.6 electron-volt. We know that the total energy is the negative of the kinetic energy, then meaning that the kinetic energy is equal to 13.6 electron-volt. We know that the total energy is equal to kinetic energy plus potential energy. Then by replacing the values of the total energy and the values of kinetic energy, then we can calculate the potential energy. By doing so, we get the potential energy, which is equal to minus 27.2 electron-volt. Moving to the third sub-question for this question. The question is telling us that the hydrogen atom in the ground state absorbs a photon. It has absorbed the photon with 12.75 electron-volt. Then the question is asking to what level is the electron promoted. So we have the hydrogen, which is at the ground state. Then it has absorbed the energy, which is 12.75 electron-volt. Then the question is asking to what level is the electron promoted after absorbing the photon with that energy. So we need to first calculate the energy at the ground state. So the energy at the ground state is equal to minus A, which is the Rydberg constant, divided by the n square, and n is 1 at the ground state. Then replacing the values, we get the energy at the ground state of minus 13.6 electron-volt. Then we calculate the energy. We have now the energy, which is equal to minus 0.85 electron-volt, equal to minus Rydberg constant, dividing with the n and the n square. So which means we need to determine this n. Determining this n, then we get n is equal to 4. Moving to the sub-question number 4. It is asking to calculate the change in energy. What is the change in energy in joule for an atom that releases a photon with a wavelength of 3.2 times 10 power negative 7 meters? So here we know the formula for the change of energy, which is equal to a Planck constant times the speed of light dividing for the wavelength. Then we can calculate the change of the energy by replacing each of the parameters there in the equation by its value. Then we get 6.21 times 10 power negative 19 joule. And the sub-question number 5 is asking calculate the frequency and the wavelength of the emitted photon when an electron drops from the n is equal to 4 to n is equal to 2 state. So in this case, then we can calculate the change in energy. After getting the change in energy, then we can calculate the wavelength. So calculating the change in energy, we get it And after calculating the change in energy, we know that the change in energy is equal to Planck constant times the frequency. Then after calculating the change in energy, we get the frequency. After getting the frequency, then we can calculate the wavelength. So replacing the value, the change in energy is equal to minus 4.07 times 10 power negative 19 joules. So this negative, it does not mean that the energy is negative, but it is indication that the energy is lost. The negative sign is to indicate that the photon is emitted, so which means we have a loss of energy. But normally the energy cannot be there, cannot be negative. We can calculate the frequency. The frequency is equal to change in energy dividing with the Planck constant. Replacing the values, then we have 6.14 times 10 power 14 hertz as the frequency. Then from the change in energy, we can also determine the wavelength, or from the frequency. So we know the wavelength is equal to hc, Planck constant, times the speed of light dividing with the change in energy. We have calculated the change in energy. Then we calculate the wavelength and we obtain 488.55 nanometer as the wavelength. So these were the question for this sub-question 23. Then next time we are going to move to question 24. Question number 24 has three sub-questions. Let's start on sub-question 1. Sub-question 1 of question 24 is asking what is the wavelength of a photon emitted when an electron goes from n equal to 6 to n equal to 2 in a nitrogen atom. So we need to calculate the wavelength. So as we know, we can calculate the energy. Then after getting the energy, then we can calculate the wavelength from the energy. The change in energy when an electron is moving from n equal to 6 to n equal to 2, then for us to calculate this change, we use this equation where we have the Rydberg constant, bracket 1 over n initial squared minus 1 over n final squared. So which means we need to replace the values and get the energy. The n initial is 6 because the electron is coming from n equal to 6 to n is equal to 2, which means n final is equal to 2. So in that case, we get the change in energy, which is equal to minus 4.84 times 10 power negative 19 joule. So energy cannot be negative, so it means this negative means that the energy is emitted. It means that there is a loss of energy. The negative sign indicates the loss of energy, indicates that the energy is emitted. So which means the emitted energy is equal to 4.84 times 10 power negative 19 joule. After getting the energy, then we know that energy is equal to the Planck constant times the frequency. Then the frequency, then we can replace the frequency with the speed of the light dividing with the wavelength. Then we can arrange the terms and get the wavelength. So which means the formula for the wavelength equal to the Planck constant times the speed of light dividing with the energy or the change in energy. Then we can replace the values and then we are going to get 410.7 nanometer. Let's move to second question of this question 24. The second sub-question is asking calculate the energy change corresponding to the transition of an electron from the n is equal to 1 to n is equal to 3. So which means the n initial is 1 and the n final is 3. So it's simple. Then we calculate the energy change using the formula and we are going to get 1.94 times 10 power negative 18 joule. So if you check, then here the energy is positive, so meaning that the electron has absorbed the energy, a particular amount of energy. So which means a photon, an electron has absorbed the photon, and that's the reason why you see that the energy is positive. So it is a transition from n equal to 1 going to n equal to 3. Then after calculating the change in energy, then we calculate the wavelength as the question is asking. The wavelength equal to hc over change in energy, which means Planck constant times the speed of the light dividing with the change in energy that you have calculated. Then we got the final answer, which is equal 102.46 nanometer. Let's go to sub-question 3. The sub-question number 3 is telling us an electron in the hydrogen atom has made a transition from energy state of the principal quantum numbers Ni to n is equal to 2 state, which means Ni is the initial state which is not known, so which need to be calculated, and the electron goes to n equal to 2 state. Then if a photon is emitted, so they are telling us that a photon is emitted, and they have given us the wavelength of the photon, which is equal to 434 nanometer. Then they are asking what is the value of Ni, so which means they are asking the initial state Ni. So for us, we have the wavelength of the photon which is emitted. Then from that wavelength we can calculate the change in energy. Calculating the change in energy equal to the Planck constant times speed of the light dividing with the wavelength. So the speed of light is known, the wavelength was given, the Planck constant also is known. Then you can calculate the change in energy. So now they are saying if the photon emitted, so then if the photon is emitted, then we need to put the negative sign. That means that there is a loss of energy. Then the formula, the change in energy will be equal to minus 4.58 times 10 power negative 19 joule. Then we replace the formula with minus sign because the energy was emitted. Of course, I told you that the energy cannot be negative. This negative sign is to indicate that there is a loss of energy. Then we need to arrange the term and we calculate the Ni. After arranging the terms in the equation, you will get the Ni equal to 25. So which means for this electron, the initial state is n equal to 5. Let's go to question 25. The question 25 is also having the 4 sub-question. Let's quickly go to sub-question number 1. Sub-question number 1 is asking what is the wavelength of the line in the Balmer series of hydrogen that is composed of transition from n is equal to 2 to from n is equal to 5 to n is equal to 2. So they have given the Rydberg constant in meta minus 1. So which means for this one we need to use 1 over wavelength as the formula. And they are asking the wavelength. Then we have the Ni, which means is equal to 5, and the Nf is equal to 2. So it's only to replace in the formula and get the answer. So replacing in the formula, they are asking what the wavelength of the line in the Balmer series of hydrogen that is called transition from n equal to 5 to n equal to 2. So which means the transition is coming from a higher level to lower level, means there is a loss of energy. So a loss of energy, then we place the negative sign to the formula. Then we arrange the term to find the wavelength that they are asking. In that case, after arranging and calculating the wavelength, we got 434 nanometer. The second sub-question, it is telling us that the Riemann series of hydrogen is made up to of those transitions made from higher level to n is equal to 1, which means the Balmer series is made up of the transition from higher level to n equal to 1, from 2 to 1, from 3 to 1, from 4 to 1. So all these transitions that are rounding to n equal to 1, these transitions are called Riemann series. Now they are asking what is the wavelength of the first, second, and the third line in Riemann series, which means the first line series is coming from 2 to 1, the second one from 3 to 1, and the third one from 4 to 1. Now they are asking the wavelength of this line. So now as long as we are having the n initial, which from, for example, if we take the first line, the first one means Ni is equal to 2 and n final is 1. From the second one, n initial is 2, is 3, and n final is 1. And from the third one, n initial is 4, and the final one is 1. So we need to use also the formula, but because they are transition from higher level to lower energy level, we need to place the negative sign on the formula, because there is a loss of energy. Then after calculating, if you calculate, for example, the first line for the transition coming from n equal to 2 to n equal to 1, then what you need to replace is to replace Ni, which is equal to 2, and Nf is equal to 1. Then rearranging the term, we get the answer of for the wavelength, which is equal to 121.54 nanometer. If you go to the second transition, which is coming from or the second line, which is coming from n is equal to 3 to n is equal to 1, we need to replace in the formula Ni is equal to 3 and N final is equal to 1. Of course, don't forget to place the negative sign, because there is a loss of energy. A transition is coming from high energy level to lower energy level, and we are going to get the wavelength, which is equal to 102.55 nanometer. For the third line, it is coming from n is equal to 4 to n is equal to 1. So we are going to replace Ni is equal to 4 and N final or Nf is equal to 1. We arrange the term and you get the wavelength, which is equal to 97.23 nanometer. The next sub-question is asking the partial series of hydrogen corresponds to electron transition from higher level to n is equal to 3. From what level do an electron that produce a wavelength is coming? So they have given the wavelength of a photon. Then after the wavelength, after giving us the wavelength, they have given also the Rydberg constant. Now they are asking the Ni. So they have given the N final is equal to 3. Then they're asking from where, from Ni, from where an electron is coming to run to n is equal to 3, when the wavelength is 1285 nanometer. Here also, we know that the electron is coming from high energy level to low energy level. We need to plus the negative sign on the formula. Then we know that the Ni is unknown, but the Nf is known is 3. Then we replace the terms, and then we sort the problem, and then we obtain the Ni that was asked. Then the electron is coming from n is equal to 5 to n is equal to 3, because we calculate and find that Ni is equal to 5. Then another sub-question, which is the last sub-question, is asking the partial series of hydrogen corresponds to transition from higher level to n is equal to 3. Then they're asking what is the shortest wavelength in that series. The shortest wavelength. Use the Rydberg constant was given. The shortest wavelength. So for us to calculate the shortest wavelength, we need to understand when do we have the short wavelength. So we know that the change in energy is equal to the Planck constant times the speed of light dividing with the wavelength. As you can see, we are going to have the short wavelength. The short wavelength when you are having the highest change in energy. Because the wavelength is equal to hc, or the Planck constant times the speed of light dividing with the change in energy. Then if this denominator, if the change in energy is high, that is where we are going to have the lowest wavelength. So then they're asking what is the shortest wavelength. This is when you have the highest energy as possible. That is where we have the change in energy is highest when the first time 1 over Ni square. So which is the first time in the bracket. So when it is turning to infinite, that is where you will have the highest energy change. Now, in that case, we will have 1 over the wavelength, which is equal to minus r over nf squared. So, with this means that these terms r times 1 over infinite squared will be 0. Then we remain with the second one. So this means that that's where we are going to have the highest energy change. Then after having the highest energy change, then we calculate the 1 over the wavelength. So we replace the N5. Then question 26 is asking if we take this energy 7.21 times 10 power negative 19 joule to remove an electron from the iron atom, then what is the maximum wavelength of light that can do this? So we have the energy, then we can calculate the wavelength. They're asking the wavelength, the maximum wavelength. Then the second sub-question is asking to calculate the energy of 1 mole of a photon of radiation with frequency. So we have the frequency, and then they are asking to calculate the energy of 1 mole. It is not energy of 1 photon, but energy of 1 mole. So a mole of photon is having more and more photons. So how many number of photon in 1 mole? So which means a number, 1 mole of photon is having the number of photon equal to the Avogadro's number. So we use this scenario. So then for the first sub-question, they're asking takes this amount of energy to remove electron from the iron atom. Then they're asking the maximum wavelength. So we arrange the term and calculate the wavelength. The wavelength equal to hc over e, the Planck constant, the speed of light dividing with the energy. So replacing the terms, then we get 276 nanometer. Going to a second sub-question. So we need to calculate the energy of 1 mole of photon with a frequency. So for here, we can calculate the energy of 1 photon. The energy of 1 photon is equal to Planck constant times the frequency. Then we get the energy of 1 photon in joule, which is equal to 33.13 times 10 power negative 20 joule. Then this is the energy of 1 photon. And 1 joule, 1 mole is not a 1 photon. So 1 mole is equal to 6.023 times 10 power 23 photons. Then to get the moles, to get the energy of a 1 mole, we need to take the energy of 1 photon, multiply with the number of photons per mole. Then by doing so, we get this amount of energy per mole of a photon. That was the second sub-question. So it means that we calculate the energy of 1 photon, then we multiply with the number of photons in one mole to get the energy of 1 mole. Then the next question is asking, question 27 is saying, if a mass of an electron is 10 power negative 26.7 kilogram and the uncertainty position is equal to 10 power negative 11 meter, then find the uncertainty velocity. The second sub-question for this question is asking, find out the accuracy in position of a particle if the uncertainty in the momentum of the particle is this one. So here we need to use the equation for uncertainty, where we have the uncertainty in position times the m times the uncertainty velocity, which is equal to h over 4p. So which means we have the uncertainty in position, we have also the mass which is equal to 10 power negative 27 kilogram. Then they're asking the uncertainty in the velocity. So we need to replace and then find delta v. So the others we have the uncertainty position was given as 10 negative 11 meter. Then we arrange the term and we get the uncertainty velocity, which will be equal to 5.28 times 10 power 3 meter per second. Going to the second sub-question, also we have the accuracy in position. Remember the mass times delta v, or mass times the uncertainty in velocity. That's what we are calling the momentum. Then that term was given. They are asking find out the accuracy in position, which means they are asking delta x, m times delta v, that is the uncertainty in the momentum. It was also given. Then we need to replace the terms. What we need also to change that the Planck constant was given in the x, we need to change into joule second. So 1 joule constant, if we are converting the joule in eric to joule a second, in that case we're going to multiply 10 power negative 7 to get joule second. Then others we can change the dp. We can change also the dp. The dp equal to 2.2 times 10 negative 4 gram centimeter second minus 1. So which means this is the change in the momentum. The momentum was given as gram centimeter second minus 1. So we need also to change to kilogram meter second minus 1. If we are changing gram to kilogram, so we are going to divide it for 1,000. Then, if you are changing centimeter to meter, we divide with 100. That's what we did. Then you obtain 2.2 times 10 power negative 9 kilojoule meter second minus 1 as the momentum. Then for us to calculate the uncertainty position, the delta x, which is equal to h divided by 4p times the momentum. Then we replace the values, then we get the change in position equal to 2.4 times 10 power negative 26 meter. The next question, which is 28, we are going to do it for the next session. We are going to do also other question regarding this kind of series of question. Let's move to question 28. Question 28 has 4 sub-questions. Let's start on sub-question 1. It's asking to derive the formula for calculating the Broglie wavelength and to explain all the terms in the equation. So, the Broglie has used the two equations. One equation from Albert Einstein relating the matter and the energy, and another equation from Max Planck which relate the energy and the quantum of wave. The Broglie has extended the two formulas. He has extended this duality of matter, wave, this wave particle duality of matter. He extended this theory, and then he has used this equation to derive the Broglie wavelength. So, which means he has equalized the two equations, mc squared equal to h times c over wavelength. So, which means he has equalized the Albert Einstein with the Max Planck equation. Then, after doing so, because in the equation of Albert Einstein and Max Planck, there is a speed of light, and normally the particles, they don't move as at the speed of light. That's why the Broglie replaced the speed of light with the velocity. He replaced the speed of light with the velocity, and then he arranged the term. He calculated the wavelength, and he found that the wavelength equal to the h divided with mv, with h as the prime constant, m as the mass of the particle, and v as the speed of the particle. Which means, looking on that equation, very small. If an electron is very small, it means this small mass will contribute to the bigger or recognized wavelength. But for the objects which are bigger, for the big object, so they will have a high mass, and having a high mass reduce the wavelength, as you can see in that formula. What you can see in that formula is that object with a high mass will have a lower wavelength, and that object with a very small mass will have a higher wavelength. So, which means that an electron which is very small, it will have a wavelength which is relevant. While for the object which are big, in that case, they will have a very negligible wavelength because they will have a higher mass. That is what the formula means. And the second sub-question is saying that an electron has a velocity of 5 times 10 power 5 meter per second. It is asking what is the wavelength in meter and in nanometer, and the mass of electron was given. So we only need to replace in the formula that you have derived the above. So the wavelength is equal to h dividing with mv, with h prime constant, m as the mass of an electron, and v as speed of electrons. Then, if we replace all these values that we are given, we get the wavelength which is equal to 1.46 nanometer. The next sub-question is asking to determine the Broglie wavelength associated with neutron. The speed was given, the speed of that neutron, and the mass of neutron was given. Also, it's the same as the question above. We need to replace the terms, but don't forget to change the mass of neutron from gram to kilogram. Then, after changing, we only substitute the values, and you get the wavelength which is equal to 0.0794 nanometer. The next sub-question is asking what is the velocity of an electron, and we have the wavelength of an electron beam, which is measured to be 900 nanometer. They are telling us that in the same beam, and uncertain the momentum is this one, and then they are asking what is the minimum uncertain position of the electron. For the first, they are asking what is the velocity of the electron. For this one, we use the formula for the Broglie wavelength, which says the wavelength is equal to h dividing with mv. Then we arrange the term and we obtain a v is equal to h dividing with wavelength times the mass. So we need to change the wavelength that was given into nanometer. We need to change it to meter. Then after changing it, then we calculate the velocity of the electron. We get, after replacing the values, we get the velocity which is equal to 809 meters per second. Then for us to obtain the change in position, the uncertainty in position, in that case we use the formula. We arrange the term. We have given the momentum. The momentum is equal to m times delta v. Then we calculate the change in we calculate the dx, or the uncertainty in moment, the uncertainty in position, because we are having the uncertainty in momentum. So which means the uncertainty in position will be equal to h dividing with 4p times delta p, with h the Planck constant, dp as the uncertainty in momentum. Then rearranging and calculating the terms and replacing the values, we get the uncertainty in the position, which is equal to 7.96 times 10 power negative 11 meter.